Hello everybody and welcome to the NPTEL online certification course on microelectronics devices to circuits. In our earlier modules and interactions, we have understood what is the meaning of propagation delay of an inverter. We have also seen how an inverter using an N channel MOSFET and a P channel MOSFET can be formed and what is the basic electrical functionality of a inverter. We have also seen what is the meaning of noise margin as far as inverter characteristics is concerned, what is the meaning of voltage transfer characteristics, how we are able to calculate the high noise margin and low noise margin and its importance in terms of digital as well as analog logic. We have also seen the various functionalities of basic inverter and the basic concept of power dissipation. In this slide or in this module, we will be actually dealing with the concept of power analysis in a much more detailed manner. So, that is what the outline of this talk is, that and therefore, it is named as power analysis part 1. Let me give you an idea about what the power analysis is all about. Generally, you must be aware of the fact that energies are always represented in form of joule or also referred to as kilowatt hour, right, and it is also defined as the measure of the ability of a system to do work or produce a change. So, therefore, no activity is possible without energy, right. So, that is the reason why we always talk about energy in terms of whenever we have an electronic circuit coming into picture, because without energy you will not be able to do any computation, you will not be able to do any logical operation. If that energy per unit time is basically power, so energy by time is basically my power, and that is what is written here. So, amount of energy required for a given unit of time is basically referred to as power. So, it might be true that I might be doing a very small amount of spending small amount of energy over a period of time, but if my time domain is very small, I could spend large power in a small interval of time, right. So, that is pretty important. When we say average power, it primarily means that the average amount of energy consumed per unit time. So, let us suppose you were consuming 5 kilowatt during the first hour, 3 kilowatt in the second hour, then 5 plus 3 8 by 2 will be 4 kilowatt will be the average power, right. So, average power is therefore defined as the power where you take the average in the time domain, right. So, two things take away here from this slide. Energy is primarily the ability to do work, or if you want to do some work you have to have energy with you. And what is power? Energy per unit time is defined as power. You might have a high power and low energy as well, right, because power is energy by time. So, if your time domain is pretty small and your time domain is relatively small where energy spending is large, you might get a large power. We have also defined the average power concept here. We now therefore define also an important term known as instantaneous power. Instantaneous power primarily means that when this t tends to 0, right. So, del E del t is my power, and when del t tends to 0 we define this to be as an instantaneous power, which means that when we are calculating power and this power we are just transient at a particular time t, we define that to be as an instantaneous power, right. Okay. So, we have two types of power, instantaneous power and average power. As I discussed with you, therefore, instantaneous power, when you want to find out P of t is exactly equals to V of t and I of t. So, voltage V of t is the voltage and I of t is the current which you see, this is the current. So, voltage into current, which is a function of time t, will give you the power here. So, V t is basically the potential difference across the component, function of time t, and I t is the component current component, right. So, electrical energy will therefore be power per unit time, power into time, sorry. So, power into time will be there. So, V into I into t will be the value of electrical energy, right. I am not going into details of this one. I think these are pretty simple basic concepts, even taught in class 12th sort of a mechanism, or even in your school days you are taught all these things, right. We define a new term also, and therefore, if you see very clearly you have a component this of power, right, and this is primarily your time t across which the power is being spent, also referred to as a delay. So, energy will also refer to as power into delay, right, and that is why it is known as a power delay product. Energy is also referred to as a power delay product, right. and this has been used for quite a long time to find out the power delay product in terms of energy. So, if you multiply the power multiplied by the delay in the signal going from primary input to the primary output, and if the power dissipation is P, then we can find out the energy is to be equals to P into D, right, and that is what standard mechanism of power and energy is all about. Therefore, in all practical examples, you will see that you have a VDD rail and you have a ground rail passing through the chip. Now, whenever you accept power, you accept power from the VDD rail, right. So, VDD rail is the rail where you are giving the voltage, a DC voltage or an AC voltage you are giving, and from this DC voltage you are dragging power and feeding it into various active components of the device, right. So, what I am trying to tell you therefore is that power is drawn from a voltage source attached to VDD pin of the chip. So, I have a VDD pin, it connects to the voltage source, and I am able to therefore have power being drawn from the voltage source at this point. We have just now discussed that the instantaneous power PT is equals to IT into VDD, right. VDD is a DC bias, so it will not be a function of time t, right. We define energy therefore is equal to 0 to t integral 0 to t PT dt, and therefore I can safely write down PT dt as IDDT VDDT, right. So, now again you can also say that since VDD is constant, you can bring it outside, and therefore I can write down energy to be equals to integral 0 to t VDD, right, into IDD t dt, right. Now, since current is a function of your time t, you will always have a energy integrated from 0 to time capital time t, where capital time t is the time period across which you are measuring the energy. Average power, as I discussed with you, is energy per unit time, and therefore if you divide this expression by t, I get this thing. So, I get VDD by t, right, VDD by t integral 0 to t IDD VT dt, right. So, we will see later on that this drain current or the IDD current is not a constant current, but it is a function of many other factors, like for example, whether the transistors are in saturation, whether they are in active mode or they are in the non-saturated state, are they working as a voltage variable resistor. Depending upon that, the value of ID will be changing. So, ID will be either linear, it will be either non-linear, or it will be saturated, right, and we should be very careful about that particular point, that where we are talking about in terms of power. Now, let me see what is the power consumption. Let us suppose that this is a MOS device, this is PMOS, right, and this is your NMOS here, right, and your input goes from 1 to 0, right. So, when it was initially 1, this was on, and therefore, CL had discharged, and now what you are doing, you are giving a 1 to 0 transition. So, once you give a 1 to 0 transition, right, then what you see very interestingly, that the voltage here falls across this path and charges my capacitor CL, and therefore, the water here rises, and therefore, you have a 0 to 1 transition taking place here, right. So, I have a 1 to 0 transition and it goes from 0 to 1, fine, and this gives you an idea about how fast or slow your design is, right. So, when you are doing it, you are actually drawing power or you are consuming power from the VDD rail, right, because charges has been drawn from the VDD rail, and you are able to therefore have this power available to you. As you can see, therefore, energy consumption is proportional to the capacitive load. Why? Because higher the value of your capacitive load, more charge it can store, and therefore, more charge can be drawn from the VDD rail, right, and therefore, you will be consuming larger amount of power from the VDD rail, right, and that is the reason that energy consumption is proportional to capacitive load. So, if you want to reduce your energy, reduce your capacitive load, once you do that, you require less amount of charge, and less amount of charge will be therefore discharged from the VDD rail, and you will have a lower energy profile available with you, but otherwise it will remain so in a larger state, right. Now, let us see what happens when your input goes from 0 to 1. So, I have initially 0 and then it goes to 1. So, initially 0 means this is on state, this is on, right, and this is off, right, and therefore, this whole CL is filled with water, which means that this CL is actually 1, voltage across the CL is actually equal to VDD, and now I go from 0 to 1, which primarily means that this goes from on to off state, and this off to it goes to off to on state. As it goes to on state, I will explain to you. Now, you see, now this discharging takes place to the ground. Why it is discharging? Because now you have a low impedance path with you in the input side, right, and therefore, you will always have this output available to you, right. And therefore, you see in a CMOS inverter or a CMOS design, one very critical aspect is that your output node is typically not a floating node, either it is either connected to VDD or it is either connected to ground, right. And that is quite an important observation at this point of time without going into the further details of it, right. And we see that it is there. So, now energy for calculation only consumed at 0 to 1 transition, when the output was 0 to 1 transition, that was the only point when you consumed energy. When the output is going from 1 to 0, you are actually dissipating energy, and you are able to dissipate energy to the environment, right, or to the heat sink, whatever you name it. Now, the idea therefore is, let us see what the idea is. The concept is that let us suppose your PMOS width was very large, right. So, if the width is very large, I will expect to get a smaller resistance. So, R on or R equivalent P will be small, and therefore, IDD will be relatively large, and as a result what will happen is that if you look very carefully, that is what is happening. When input is going from 0 to 1, the output is going from 1 to 0, right. I will just show it to you. It go to 1 to 0, right, but the rate at which it goes from 1 to 0 is very fast, sorry 0 to 1, I am sorry 0 to 1, 0 to 1. So, this is going from 0 to 1 to 0, this is going from 1 to 0, and therefore, output is going to 0 to 1, right. Now, 0 to 1 means basically that if you look very carefully, look at the first figure here, look at the first figure here. So, it was initially unfilled, which means it was initially 0. Now, you start giving your voltage, this starts to fill up, means the voltage is rising, and the voltage is rising like this. After that, it remains constant here. Same concept applies here also, but only thing is that here W by L ratio for the PMOS is smaller. So, this has got a bigger width, W by L is larger, and this is W by L is smaller, right. So, W by L 1, let us suppose 2. So, W by L 1 is much larger as compared to W by L 2, primarily meaning that you allow larger currents to flow and charge your CL, therefore, the rate of charging is smaller and you are able to achieve 1 very fast, right. But when your W by L as ratio is small, you allow larger amount of time to move, and therefore, inverter 1 is faster, right, inverter sorry I am sorry. So, the inverter 1 is faster. So, why it is faster? Because I am able to do a large amount of transfer within a short period of time, which means that since the delay is lower now, I would expect to see the energy to be high, and that is true also, because for a smaller duration of time you are sending a large amount of charge. So, the energy is large. So, what happens is that the delay though is reducing, but the energy is basically typically very large in this case, whereas in this case delay is large, right, and therefore, energy is reduced. In the second case W by L ratios are very small for the pull up device, in this case PMOS devices. Now, therefore, there are two approaches which is available with us. Now, if you look at the approach, this is power versus time, right. The area under the graph is basically your energy, P, because P into T is basically your energy, right. So, this is E1 and this is E2. Both see if you look at it in that way, both E1 equals to E2. It primarily meaning that the energy consumed by both the transistors, please understand, both the first transistor and the second transistor is large, but the first transistor does this energy at a shorter duration of time, whereas in the second one it does it larger duration of time, right, and this is a larger duration of time it is doing it, and this is doing it at a shorter duration of time, right. As a result, so energy is the area under the curve, right. So, energy is same because the area is same, but then you are dissipating more amount of power here in the first case, the reason being you are doing it at a smaller time domain. So, this is T1 T2, right, and this is T3 and T4. Now, if I subtract T2 minus T1, it is much smaller as compared to T4 minus T3. As a result, this energy E1 so the power is much larger as compared to the second power, right. Okay. So, we write down therefore power into delay equals to energy, right. So, energy is equals to power into delay, right. So, this is what a standard mechanism which we follow. Now, let me therefore come to the matrix. The problem of energy dissipation is that the battery life will be in hours rather than minutes. if I reduce the power dissipation, and it sets the packaging limit. Why packaging limit? Because the reason being, if it is highly dissipative in nature, you should have proper heat sinks in the packaging, so that you are not able to let the heat or the power dissipate within the chip, but outside the chip, right. So, your packaging limits are set in that, right. Peak power is defined as the power which is peaking at any particular time t, and therefore depends upon the wiring design as well as a noise margin and reliability analysis. So, we will not go into details of this one, but primarily therefore, if you look very carefully, I can have therefore two energies which are equal, but in one case the power will be higher and in other case the power will be lower, right. That is what we know as a basic concept which you see here. So, therefore, the quality criteria power delay product, as we discussed, was an energy. PdP was equals to P start Tp. P is the power dissipated multiplied by Tp, which is the propagation delay, right. So, you see two designs can have the same PdP even if Tp is 1 year. I hope you understand. For example, in one case the Tp is 1 year, in another case Tp is basically say 1 month or whatever small value. Then for the same PdP, this will have a lower power, whereas this will have a much higher power, right. So, if you are able to achieve a functionality within a small duration of time, you end up having a larger energy or larger power, whereas if you do the same computation for a larger period of time, you are spending less amount of power. So, power depends not only on the total energy, but also on the time domain analysis of each one of them, right, and that is quite an interesting one. So, where does the power go in a CMOS? That is pretty intriguing question, and people have been asking this question for a long time, and there is a straight answer available here also. We have three types of power consumptions. We have got dynamic power consumption, we have short circuit power consumption, short circuit and leakage. So, you have dynamic power, we have short circuit and we have leakage, right. So, dynamic, as the name suggests, it is basically not fixed, but goes on changing with respect to time, which means that charging and discharging of the capacitor of the design is defined as the dynamic power consumption. So, faster the charging discharging, more will be the power available with you, or more will the power dissipated for you. Then of course, as I discussed with you in a previous turn, you will have a short circuit power between supply rail and ground during switching, and there will be also some leakage current, which is primarily your reverse leakage current, also due to Zener leakage current and so on and so forth, and the transistors will show you a drop here, right. So, these are some of the problem areas which you will face, the last two, and the major contribution which this will give you is basically, I will have a larger dynamic power dissipation or a smaller dynamic power dissipation, I will have a larger or a smaller short circuit power dissipation, and we also have a smaller leakage which is basically a subthreshold leakage with us, right, and this is what we get from here. Now, let me come to the again the basic dynamics or the basic equations of dynamic power dissipation, and if you remember correctly, half CL VDD square you are taking from the VDD rail, and then you are pushing the half CL VDD square into the ground, right, and therefore, for a one cycle you are actually taking half plus half, which is actually exactly equals to CL VDD square, and that is the reason you get CL VDD square as the dynamic power, initial dynamic power. Then what you do is you multiply this with P0 to 1, P0 to 1 is the probability that you get 0 to 1 switching done in the circuitry. Easier said than done, because you do not have any control over the circuitry, and the second thing is that if you do a 0 to 1 transition, you will automatically have almost half the maximum frequency of operation, and that is the reason the probability for 0 to 1 switch of output is kept at the last point. F is the clock frequency and alpha is the activity. We have already discussed the activity concept in the previous turn. So, for example, if you have a clock, the clock will have surely an activity, and that therefore will have an activity equals to 1. If you do not have a clock, but you have some complex logic gate, maybe your alpha will be 0.75 and so on and so forth. So, on two factors primarily your dynamic power depends, and that is known as the frequency of operation, as well as on the probability that the output will go from 0 to 1, fine. That is what is dynamic power dissipation is all about. Now, let me come to, therefore, as I was discussing with you, you get 0 to 1, and this f of 0 to 1 is defined as alpha into f. Please understand that f of 0 to 1 is basically the meaning of functionality from 0 to 1 is defined as alpha multiplied by f. Alpha is the activity factor and f is the frequency of operation of the device, right, and f is the clock frequency. Let us look at the dynamic power dissipation as I discussed with you, CL VDD square star the probability that you are going from 0 to 1 so 0 to 1 multiplied by f, where f is the frequency of operation of the device. As I discussed with you, data dependent, why is it data dependent, and it is a function of switching activity. Why? The reason is it is data dependent in the sense that if your both inputs are 1 1, right, and you have an AND gate also, logic is also there, then your pull down network will be fully activated and your output will be very strong 1 to 0 transition. So, which means that it is very difficult for you to go from 0 to 1 transition, and the reason being that if your data depends on the functionality of the switching circuit activity, right, which means that how the input how the output goes high or low will depend upon whether the device is switched on or off, right, and that is the problem area of the data being inserted here. Let me come to the next part, that is the short circuit power dissipation or consumption. We have just now discussed about with you the dynamic power, which primarily depends upon the frequency of operation and the capacitive charge. We now define short circuit. We have already discussed this point earlier also, but I will delve it in slightly more detail. If you remember, we were discussing that during the on state, when your device was on, we define the device to be in the on state, and we also say that the output will be switched off, right, because typical inverter characteristics we discussed yesterday, right, something like this. So, when your input is low, output is high, if input is high, output is low, right, input is high, output is low. Now, if you are biasing your device here or here, you will have a problem, and the problem is that you will have now no current flow through it, but there will be a loss in the voltage value. Somewhere here in the middle, right, where you have switching thresholds available approximately equals to VDD by 2, then your NMOS and PMOS, this is your PMOS, right, and this is NMOS, these two are equally on, getting my point, which means that both are equally on, which primarily means that both the transistors will be able to pull the charge carriers from the peripheral onto the capacitive load, fine, is it okay. So, that is the reason the short circuit power dissipation is very low in case of a simple CMOS inverter, right, and this is what is an interesting idea. Now, as I discussed with you, there is a direct path between VDD and ground. So, I write VDD into ISC, ISC is the short circuit current multiplied by P01, P01 is the probability that the output goes from 0 to 1, and then you have a probability the output goes from 1 to 0, right. So, we are actually not interested in this domain, we are rather interested in this domain, which means to say is that given a complex logic gate, can you find the probability that the output goes from 0 to 1. So, there is a, we will do it as we move along, but that is what it is all about here, right. So, short circuit depends upon all these values. Let me come to therefore the leakage. So, I had saturation in which the gate voltage was very large or very small, and therefore, the output will be either switched on or switched off. The second issue which came up was that of the static power dissipation or yes, the static power dissipation, short circuit power dissipation. When both the devices are equally on, you will have a direct path between the two, end up with last leakage power, which is a subthreshold leakage, right. So, when your gate voltage is just smaller than the threshold voltage of the device, there will be large carrier movement which will be available, which will result in a subthreshold leakage, right. We will not go further than this, but I can write a P peak equals to I peak into VDD. Now, I peak can be written as I sub plus I gate, right, multiplied by VDD, fine. So, this is what an important this thing we get. Next we get the power equation. The power equation, as I discussed with you, CLF times VDD square is your dynamic power dissipation. We have VDD times I peak as the, so this is basically your, so this is your dynamic, right, this is your short circuit power dissipation, this is your not short circuit, this is a short circuit power dissipation, and this is basically your power dissipation by virtue of leaking. So, I have a leakage available with me. Now, if you see carefully in all these discussions or all these ideas, you will appreciate that that if you look carefully, it tells me that the total power dissipation can be broken down into 3 parts, and those 3 parts are mentioned in this region, that some of them will be so what I tell you is that if you have some voltage variations, your VDD will change and your P will change. Similarly, if your probability of 0 to 1 and 1 to 0, if it happens, you will obviously get added up with the total probability, and that is the reason you will get a higher energy. Similarly, VDD into I league will also give you a higher power. Now, the dynamic power is approximately 40 to 70% of the total power, and it is decreasing yearly, and that is sort of a good thing for us. The second thing is short circuit power is relatively small, it is approximately 10% of the total total charge available, and is decreasing. So, this is also decreasing, this is also decreasing. What is increasing is basically my leakage power. Because of the reduced dimension, you do have a larger chance of the charge carriers being leaking, and that is the reason it is leaking by 20 to 50%, and here where people are actually concentrating large for optimizing power, right. As I discussed with you dynamic powering, I will not go into further details of it, but I will give you a brief idea about dynamic power dissipation. It is actually VDD by T, FSW, T times FSW is basically the frequency of operation or number of times the output changes before time T, right, and this is what is known as this thing. We come to dynamic power dissipation given by C VDD square times F of SW. F of SW is the frequency of your short wave, the frequency of your wave, right. Now, suppose the system has a system clock of F, right, then F CW is SW is, let us suppose, alpha into F, where alpha is the activity factor. Now, if signal is a clock, as I discussed with you, alpha will be equals to 1, and therefore, I will get C VDD square multiplied by F as equals to P dynamic, right. Similarly, but if the signal switches once per cycle, so there is a 1 0 to 1 transition between the one full cycle of this input, we can give you an alpha equals to 0.5 or 1 by 2, right. For static gates, typically alpha will depend upon the value of the static gates, it is equals to 0.1, and if you are using a dynamic gate, it is 0.5 or 1 by 2, right. So, we have seen one important point of activity factor is that activity factor depends upon the type of logic level you are deciding as well as on the structure which you are deciding, right. Now, let me come to the static power. We have already discussed the static power. The static power is primarily the power which is dissipated across the board or across the device when you do not give any dynamic power. So, which means that when you do not give any VDD at that point of time, whenever the device is in the off state maybe or just simply off, you have leakage currents available or you have a subthreshold current available, which basically gives you a larger power. So, this is a larger power, IDS equals to IDS 0, IDS 0 at V equals to 0, the amount of current flowing is given as IDS 0, and we get this big equation available here, and I got the expression for threshold voltage. So, this is the expression for threshold voltage, right, and that is quite an interesting result which we get. But if you forget about this one, the last one, you will see that with increasing VDS, e to the power minus VDS will go on decreasing, and therefore 1 minus that will go on increasing, and as a result you will get a larger IDS value, right. So, mathematically it seems that this should work fine. Now, let us see how can you reduce power, right, that is the most important part which we learn from all these things. The first thing is that reduce your clock gating, right, reduce your clock gating, or you put it into sleep mode. So, when the system is not working, either you put it into sleep mode or you put your the devices into clock gating. So, once you put through clock gating, it primarily tells me that you can reduce the value of alpha. C should be small, and therefore, you do not have to work with large wires, it should be small in length, and that will give you a small transistor based design, right. You should also work with the lowest suitable voltage in all sense, and the reason being, if it is not, the power dissipation levels will be typically very large, and you require the lowest possible frequency. So, possible frequency, voltage, power, and you should actually therefore rely on small transistors and short wires, right, and this takes care of our low design concept. So, how do you design, how do you reduce your dynamic power? As I discussed with you, alpha, C capacitance, VDD, which is the lowest suitable voltage available to you, and alpha F is lowest suitable frequency, right. How do you, so this is dynamic. How do you reduce static power? Selectively use ratioed logic, selectively use low VT devices, right. You will have leakage reduction provided you arrive at stacked devices, body bias and temperature. So, what you see is that I can reduce static power by using certain changes in the circuits itself, making it ratioed logic, whereas if I want to reduce dynamic power or want to reduce the dynamic power to a bare minimum, I need to concentrate primarily on for the purpose of reduction on the dynamic part of it. Now, if you look carefully, how do I lower my dynamic effect? So, since QDD has a quadratic influence, so therefore, even if you double your VSS, which is doubling your power supply, that will lower your power dissipation by 1/4, right, and that is quite an interesting phenomena people have observed. Okay. So, lowering your CL, lowering CL of course will be meaning that you will be able to improve your performance, because when your capacitive load reduces, you achieve a much better performance with you. And now, reducing the switching activity, switching activity is again defined as the probability of 0 to 1 multiplied by frequency of operation, right. So, this is the probability that the girl had the probability that you have got is 0 to 1. Now, 0 to 1 transitions are power consuming transitions, and that multiplied by F will give you the frequency of 0 to 1 transition in this case, right. Now, let me come to the transistor sizing concepts. So, if you have a small W, which means the width is small, I would expect to see of course a lower capacitance, because small W primarily means that the area under this thing gate is very small, and therefore you require a lower capacitance, whereas if you make your capacitance higher and higher, I obviously at larger W I get a higher capacitance, right, and therefore this restricts my 3 dB bandwidth and so on and so forth. What happens if you want to work at higher voltages, and the reason is that sometimes my requirement is not high speed by high performance, which means that I can't sacrifice on the performance, and therefore what I do, I increase the value of VDD. Once I increase the value of VDD, I make it larger, the performance increases, at the same instant of time the power dissipation also becomes large, right. So, this is methodology which people use, that they try to do what is known as an adaptive scaling in terms of this thing, in terms of both VSS and in terms of other devices as well, right. So, I will not go into details of this one, but just so to give you an idea, if you look at this graph, it is between the PDP, power delay product, versus the delay, right. So, if you see as the delay increases, the PDP also goes on increasing for all the design, which means that you did not contribute to the design beyond a particular time limit, and therefore you see it is actually getting reduced drastically. For the conventional static CMOS, this is the equation or the graph of power design failure, and for non-standard ones, these are the case of the design available with you. So, this gives you a best logic style for input output combination, and gives you an idea about how this works for 8. So, this example is for an 8-bit adder. So, I use an 8-bit adder in a 2 micron CMOS technology, and I got these are the outputs. So, these dots are basically your output available to you for a PDP versus delay. So, when your delay is 30 microsecond or nanosecond, I will see this to be equals to approximately 50 PDP of picojoules, right. As you make your delay large, this PDP will fall down, and that is one of the major areas or advantages of this system. As you can see, therefore, as the voltage decreases, the power delay product improves. The best logic style minimizes power delay product for a given delay constraints. This is the example. Okay. You can achieve a new logic style and reduce the power, but that is way beyond the scope of this work. So, we have learned two things. We have learned in this chapter that we have learned power dissipation as well as the concept of delay, right, and what is the meaning of PDP and EDP. With these words, let me finish off today's lecture, and when we may meet next time, we will do something else regarding the logic design. Okay. Thank you very much.